Now we'll say some things about direct current and alternating current. A circuit like this one, a battery connected to a light bulb, that uses what we call direct current, and that's abbreviated DC, direct current. And what that means is that the electrons come out of the battery and they flow around this circuit in one direction, and they just continuously flow in one direction. The direction never changes. And batteries like this produce direct current. The electricity that the power company provides, though, is a little bit more complicated. It's alternating current, what we call AC. And in alternating current, the direction of the current flow repeatedly reverses. And I'll try to illustrate this with a little picture here. Suppose here's the electrical outlet on your wall, and you plug something in. So plug plugs in here and runs over, say, to a fan. Say you have an electric fan here, and the fan might look something like this with the blades that spin around. And this electric wire here, remember, is really two wires. So I'll draw the second wire in here beside the first one. It's really two wires wrapped up in some plastic insulation. But what happens is electricity flows down one wire to the fan, and it goes through the fan, and the energy of the electrons in this case gets converted to kinetic energy. The blades of the fan spin. And then so the electrons go up there to the motor. The motor's up in the top part. And there's wiring running through the base of the fan up there to the motor. And then the electrons come back down and go back through the other wire back into the wall. But they only travel like that for a short amount of time. They travel like that just a little bit of distance, and then they stop and switch direction and go back the other way. And then they stop again and switch direction and go back the other way. And so they're really switching, the direction is really switching back and forth. So if you were to just look at one little section of wire and you could see the electrons moving, they'd be moving one direction and then they'd be going the other way, and then back and forth and back and forth like that, and they would switch directions like that 60 times per second. They switch directions at a frequency of 60 hertz, at least in the United States it's 60 hertz. In other countries it's at different frequencies. But in the United States, the standard household electricity is 120 volts and 60 hertz. And you can look on the back or the bottom of just about any electrical device and see a little label that describes the electricity that the device needs. So if you have a fan like this and you pick it up and look on the bottom, for example, or maybe back here on the back of the motor, there's usually a little printed label that says 110 to 120 volts at 60 hertz or something like that. It describes the electrical specifications that this device was designed for. You look at the back of a stereo or a television, you'll always find that. And if it was made to operate in the United States, it would work with 120 volts at 60 hertz, a frequency of oscillation at 60 hertz. That means there's one complete back and forth motion 60 times every second. In Europe, I believe most of continental Europe is on 220 volts at 50 hertz. And so electrical devices that are designed for use in Europe don't work with the electricity in the United States. And the other way around too. If you have something made in the United States and you travel over to Europe and you take it with you, there's a good chance that it won't work with the electricity over there. And in fact, the plugs are even a different shape, so that you can't take the plug that's designed to go in the wall socket in America and plug an American device into the wall in Europe, because doing so would likely damage or ruin the device. And so you can buy these little adapters that you can plug in and that will convert the voltage and the frequency to the one that you need. So say if you travel to another country and you take an electric razor with you or something like that, and or a laptop computer and you have a power adapter for it, you can plug it in, but you use this little adapter to convert the power to the power that your device uses, the voltage and frequency that your device needs. And other countries are at other frequencies. Although most of the world is on 230 or 220, somewhere around there at 50 hertz. The United States is in some cases the odd man out here. Kind of like we're still in the English system while most of the world is on the metric system. Most of the world has different electricity than the United States does too. Well, the question arises, why do we have alternating current? Why don't we just stick with direct current that seems to be a lot simpler? Why do we have to have this back and forth motion of the electricity? Well, the reason is it's much cheaper to produce and especially to transmit the alternating current to your home. The direct current works well for batteries, for some the situation where you need a portable source of power like a battery. But if you're going to produce electricity on a large scale and transmit it large distances, and that's what they're doing when they power a neighborhood or a city or a state, they're producing massive amounts of electricity and transmitting it through the power grid over a very wide area over large distances. When you do that, the alternating current is much cheaper. Um, I don't know the exact number off the top of my head, but I think it would be thousands or maybe even millions of times cheaper. You could do the calculation, it wouldn't be hard. You would just take something like, say, your refrigerator and think about how many little 1.5 volt batteries it would take to run your refrigerator, and think how long they would last and how much it would cost to replace those constantly. And then think about how much you actually pay with electricity from the power company. And it's vastly more efficient to use alternating current. And that's exactly why they produce alternating current, because it's cheaper to produce and transmit. Now, most of the things that you actually plug into the wall actually use direct current. Like, say you have a little laptop computer here, and what it runs on is direct current. So here's your laptop. And when you plug it into the wall, what you're really plugging in is this little power supply that plugs into the wall. That's the outlet there. And this power supply, this transformer, takes the current that the 120 volts, 60 hertz alternating current, and produces direct current to run to your laptop. Or even if you have a desktop computer, one of the things in, say, a tower case like this, say here's a computer and you plug it into the wall, the plug comes in back. Up here in the top of the box, inside the box, there's this power supply that sits here, and the 120 volts alternating current comes into the power supply, and then there's all these wires that run in here to power your hard drive or your CD-ROM or your DVD or the other things inside the computer. But the power supply here converts the 120 volts alternating current from the wall into direct current at 5 volts or 3 volts or whatever all the little components inside the computer use. So the things that we typically use actually run on direct current in most cases, and there's some kind of power supply that converts the electricity from the alternating current that the power company gives us into the direct current that the device needs. And at the same time, those power supplies or transformers usually adjust the voltage as well, taking it from 120 volts down to a lower voltage used by the particular electrical device.